Hi kids, this is Chapter 6, Lesson 6, and this lesson continues to talk about the distributive property which we looked at in the lab last lesson. So, just as a reminder, the distributive property, we learned this in the lab, that you can represent the distributive property by finding the area model of one large rectangle, or you can rewrite it as the sum of two smaller rectangles, and that demonstrates the distributive property. So here's what we looked at in the lab. If you have, and I'm going to use variables this time, and no numbers, all variables. If you have a large or a long skinny rectangle, you can find the area by this dimension multiplied by this dimension. But you can also find the total by finding the area of these two rectangles You can find the area of one long skinny rectangle, or you can find the area of this rectangle and combine it with the area of this rectangle, and that demonstrates the distributive property. So yesterday we had numbers. This is all variables this time, but you can see the pattern. In the lab, this was the 3 kids going to the fair and the concert. That's the 3 kids. This was getting into the fair, that total, $6. And this was the concert, the $22. So with variables, this is what it looks like. This multiplied by this, A times B plus C put together, can be rewritten as A times B, remember 2 variables right next to each other means they're being multiplied, plus A times C. So this right here is the distributive property. I'm going to highlight that. So this is the distributive property. And now we're going to look at the rest of this lesson using the distributive property to solve some problems. First one we're going to do is rewrite this expression, 4 times x plus 3, using the distributive property. So what does that look like? 4 times x plus 3. Yesterday I taught you how to use, in the last lab, how to use algebra tiles. We're going to do that again. X plus 3. Remember that the variables are the long skinny algebra tiles, the fries, and the numbers are the little tiny squares or the nuggets. So this x plus 3 would look like this. There's a fry and 3 nuggets. X plus 3. Well, I've got 4 of those, 4 times this thing. So my model would look like that. 4 times x plus 3. And remember, I told you that you can't put together nuggets and fries. They are 2 separate things. But I could rearrange my fries and nuggets into one large group. All the fries together and all the nuggets together, those can be combined. So this picture right here, x plus 3 times 4, this 4 out here means 4 times this thing on the inside. I can rewrite that. If I put all my fries together, it would look like this. If I combine all my fries together, I would have 4 x's. I put all my nuggets together, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nuggets. And this follows the exact same pattern as the distributive property. You can see how these things match up. A, B multiplied together here, 4 times x is 4x. And then AC right here being multiplied together, that turns into 4 times 3, which is 12. But a lot of kids find building the actual models very helpful. So use your algebra tiles until you really start to discover this pattern. The word distribute means to pass out. If I said to the class, I'm going to distribute your tests, that means I'm going to pass them out. This A is being distributed to the things on the inside, is another way to think about the distributive property. A is being multiplied by times B, which is that, and A is also being distributed or multiplied by C, which is this. So that is another way you can think about the distributive property. This thing out here is being distributed to all the items on the inside, and that's how it's rewritten on the equivalent expression on that side. Okay, a couple more examples. Find 9 times 8 2/3 using the distributive property. In your book, the practice, it sometimes says find these things mentally. If it says mentally, for today, we're going to use the distributive property is what we are doing. So let me rewrite our problem here. 9 times 8 2/3. And 8 2/3 is another way of saying 8 and 2/3. It's also 8 plus 2/3. We just don't write the plus. So it's really an example of the distributive property. So we are going to distribute the 9 times the 8 and the 9 times the 2/3. 9 times 8 is 72, and 9 times 2/3. We learned how to solve that kind of problem earlier this year. Put a 1 under that. We can simplify the 3 and the 9. How many 3's go into 3? 1. How many 3's go into 9 is 3. So we wind up with 6 over 1, which is 6. And then finally, we just have to combine these two together. 72 plus 6 makes 78 would be our answer. So let's get some highlighting to show what we just did. So 9 times the 8, and that's this part. That would be the equivalent of that part on the distributive property. And then we did 9 times 2/3, which was right here. which is this part of the distributive property. So there is an example of using the distributive property. Another quick example, 8 times 57. This is not written in distributive property form yet. However, you can break up the 57 and then use the distributive property to solve this. So 8 times, instead of 57, I'm going to break this up into numbers that I can make it easier to solve this problem. 57 is a 50 plus 7. 57 is the same thing as 50 plus 7. Now I've got a number that ends in 0 that's good to use for mental math, and a single digit number. So now I could do the same thing, distributive property, 8 distributed to the 50 and 8 distributed to the 7. So we're going to solve 8 times 50 and 8 times 7 and put those two amounts together. 8 times 50 is 8 times 5 is 40, add a 0, 400. 8 times 7 is 56, and then just like in this example, we put those together, combine, add. 456 would be our answer. Again, using the distributive property to solve something mentally. So 8 times the 50, 8 was distributed to the 50, and 8 was distributed to the 7, 8 times 7. And then we combine those two amounts. Again, all of these are examples of the distributive property in different forms. Okay, the last type of problem you're going to practice today is something called factor the expression. Okay, when the word factor, it's that you should think multiplying. Factors are things that are being multiplied together. So I would put a little note here that means multiplying. Factor the expression. And our example we're going to walk through is 54 plus 24. This is nothing's being multiplied here. It's a sum, 54 plus 24. But we are going to factor this expression. That means we're going to change it into two things being multiplied. Now, this is what the structure that we are going to get. We're going to change this expression into something that looks like this. I'm just going to put blanks because I don't know what they are yet. Some number out here, right next to a parenthesis, which means they're being multiplied, and then a sum on the inside. Now, hopefully, you can look at this and recognize that that is actually this right here. It is the distributive property. What we're doing is kind of going backwards. From this, how can we go and create this expression? That's factoring an expression. You've got something like this over here. How can we create that? So here's the strategy. If you have 54 plus 24, and we're building on stuff that we did earlier in the year, here's what you do. You make a factor tree for 54. I know we did this a while back. What two numbers multiply together to make 54? Lots of different options. I'm going to do 6 times 9. How do I break down 6 and 9? Do they break down? Yes, they do. 6 breaks down into 3 times 2. Those can't break down anymore, so I circle the numbers when they can't break down anymore, when they are prime. 9 breaks into 3 times 3. So that is the factor tree for 54, and this is the factorization of 54. I'm going to rewrite the numbers just in order. I've got 3, 2, 3, 3. So here is the prime factorization for 54. 2 times 3 makes 6. 6 times 3 is 18. 18 times 3 makes 54. I'm going to do the same thing for 24. Make a factor tree for 24. Again, lots of options. 4 times 6 jumps into my head first. 4 breaks down into 2 times 2. 2's are prime. 6 breaks down into 3 times 2. Those are prime. Then I'm going to put these all in order. 2 times 2, and I've got another 2 there, and a 3. So something we did earlier in the year, prime factor tree, making the prime factorization. Okay, so that part's not new. Here's the new part. Remember I told you that this is the form your answer should be in. So this is what you're trying to create. I'll highlight it right here. You want an expression that looks like that. Here's how you get it using these two factorizations. So over here, I'm going to copy this structure, a number multiplied by a sum. So again, this right here, that's it, same thing. Here's how I use the factorizations to get there. I look at this factorization, I look at this factorization. What numbers are in both? 2, this 2 matches up with that 2. This 3 matches up with that 3. Those two factors, whatever common factors you've got in this factorization and this one, go right here and you multiply those together. So 2 times 3, I got those from right here. This number is a 6. 2 times 3 makes 6. So again, you may need to go back and rewatch this part. This is something we haven't done and it's a little bit tricky, but if you come back and rewatch this, I think, and you follow this structure and make the factor trees, I think you'll be able to do it. Okay, next. What numbers do I have left on this factorization? I've got 3 times 3 left. Well, what is 3 times 3? That is a 9. And how did I get that 9? I'll write it right there. I got that from the leftover factors from this factorization. What do I have left from 24? I've got 2 times 2. That is going to be this number. That is 4. So this is our answer. Factor the expression 54 plus 24. This is here is our factor. This expression factored would be 6 times 9 plus 4. We could also check it. What's 9 plus 4? If we do that math, get 13, multiply that by 6, that would be the same thing as 54 plus 24 if you were going to verify. Okay, I know that this part's new. Please re-watch this if you get to factor the expression and you're not sure. But really, it's factor trees, and then just re-watch, look at the pattern here, pulling out the common factors. That's this number. The leftover factors here make this one. The leftover factors here make that number. Okay, that does it for Lesson 6. Here is your hidden treasure puzzle. Chapter 6, Lesson 6. If you can solve that, and you've got the lesson done and all the notes for Chapter 6, you can be the winner. That's it for Lesson 6. I'll see you real soon for Lesson 7.